Okay, thank you very much for the invitation to this great place and to the great conference. Actually, the standards are now so high that I wouldn't dare anymore to organize a conference in Europe. Okay, so my subject is minimal models in scalar geometry, and we have already heard about the minimal models in algebraic geometry. For instance, in the talk of Mori. And yeah, so my plan is as follows. Of course, I will say something, what is a minimal model program, especially in scalar geometry. And well, we'll only spend 1 minute or so to say something on surfaces, just to be complete. And of course, I will say a little bit on the projective case in higher dimensions. And then what should be the analog in the scalar case. And yeah, what are the additional problems in the scalar case? I mean, it will be clear that the methods in the projective case cannot work in the scalar case in general. And also how to overcome these obstacles. So the aim is, so to speak, to give a picture how the minimal model program works for scalar threefolds. Okay, and yeah, I mean, if you've heard the talk of Mori, or anyway are familiar with the minimal model program, it is clear that we cannot just deal with smooth scalar manifolds. So we need singularities. And the question is, what is a singular scalar space? So I will give the definition of a singular scalar space. So I take an irreducible normal complex space. And then I say that X is scalar if, first of all, you have a scalar form on the smooth locus. But of course, this is not sufficient. Yeah, you have to see something, what's going on near the singularities. So then we require that if you take a singular point, then you should have an open neighborhood, V, of the point X, and a closed embedding in some open set in Cn. So this exists because we have a complex space. And then I require that there is a scalar form U. So U is an open set in Cn. So if you restrict this eta, the scalar form on U, to V, and of course to the smooth, then you get the original omega. So this definition was already given in 1962 by Howard. So this is the category we are talking about. So then, of course, the canonical bundle plays a role. So what is a canonical bundle in this setting? Of course, if you complex manifold, you just take the canonical bundle, the determinant of the cotangent bundle, or I mean, I will usually don't distinguish between line bundles and locally free sheaves as usual. So you have the sheaf of holomorphic n forms. N is the dimension of X. So what do you do in the normal, in the case of a normal complex space? Yeah, the canonical bundle. I should not speak about the canonical bundle. I should speak of the canonical sheaf in principle. Ox of Kx is defined as follows. First of all, you take the smooth locus. So there you have the sheaf of holomorphic n forms. Then you have this embedding J from the smooth locus to X itself. And then you push forward the sheaf of n forms. And then it's not very difficult to see that this is a coherent sheaf and it's actually reflexive. So this is a sheaf, so to speak, we are dealing with. And yeah, but I mean, as you know from the MMP in the algebraic case, we need some additional condition on the canonical sheaf. Namely, we need that some multiple, so to speak, is locally free. So I say that Kx is Q Cartier if and only if the following holds. You take this sheaf Ox of Kx, take the mth tensor product and make it again reflexive. and this should be locally free. So this definition of to be Q-Cartier is linguistically a little bit strange, because one should emphasize that the canonical sheaf, canonical bundle, is not a Cartier, is not a divisor or Q divisor anymore. Yeah, because you have a reflexive sheaf on a complex space, and it's not at all clear, or in general not true, that we have a meromorphic section. So it's not coming from a divisor. It's for some M. If there exists some M such that this is locally free. Okay. Then I need also to introduce some notions in the Kähler case, which you know from the algebraic case. So if you have a normal projective variety and a line bundle, or Cartier divisor or locally free sheaf of rank 1 on X, then of course we say that L is Neff if and only if L on any curve is non-negative. Yeah, so this is the usual definition of a Neff line bundle, Neff sheaf. But of course, in the analytic case, this is not suitable, because you have too few curves. Yeah, if you have a general torus, for instance, you have no curve at all. So this definition, you can define it, but it doesn't make much sense. So instead, we would say that if you have a line bundle, then L is Neff if and only if the first Chern class is in the closure of the Kähler cone. And I will explain this a little bit more in a few minutes. Okay. So the Kähler cone, what is the Kähler cone? Let's look at the smooth case, for instance. The Kähler cone is the cone in H2XR generated by classes of the Kähler forms. This makes even sense in the normal setting. Yeah, you can still define the class, but it will be a little bit more precise a little bit later. And of course, if you think of smooth Kähler manifold, then the Kähler cone sits inside H11 intersected with H2XR. So this means that the first Chern class is represented by something which is in the closure of the Kähler form, Kähler cone. Yeah, but it's not a priori not so clear what sits on the boundary of the Kähler cone. Yeah. Okay. So now I have to speak about cones, as in the projective case. So NE bar is just the closed cone in H2XR generated by the classes of the irreducible curves. So this is just a definition from algebraic geometry. But of course, as I said, this cone can be very small, too small to deal with. Yeah, if I have no curves, then this cone is 0. So we need some bigger cone. So what is this bigger cone? This will be the cone NA bar X. So this is a closed cone in a mutable sense, which I explain in a minute, generated by the classes of positive closed currents of bidimension 1, 1. So the principle is that instead of looking at cones, instead of looking at curves, we look at the more general objects, namely currents. And any curve is actually a current, or can be identified with a current, namely the current of integration over the curve. So this will be the substitute of NE bar in the Kähler setting. And on the other side, yeah, N1X is a space of closed 1-1 forms or currents with local potentials. This means locally is I dd bar of something. Modular forms, global forms of the type I dd bar U. And N lower star of X, this will be the space of real closed by dimension 1, 1, modulo the following relation. I say that if you have two currents, T1 and T2, that they are equivalent, if and only if you evaluate it on any form phi, they are equal, where phi is a closed 1, 1 form with local potentials. So this is, so to speak, I mean, in the algebraic case, we have this Néron-Severi spaces, n1 of x and lower 1 of x, and now we get a larger space. Okay. X is compact. Yeah. I mean, we can make some definitions also in the non-compact case, but and well, n1 of x is often also called n11 BC, where BC stands for Böttcher cohomology, especially in the smooth case. And if you have if x has rational singularities, which will be always the case in our setting, then you have a canonical injection n1 of x inside H2XR. So any element in n1 of x really can be viewed as a de Rham class. And moreover, we have a natural duality between n1 and upper 1 of x to n lower 1 of x dual, as in the projective case. So then NA of, if I give a proper definition, NAX is the closed cone in n lower 1 of x generated by the positive closed currents of bidimension 1. And then also to speak on the other side of, so to speak, codimension 1 about Neff classes. So what is a Neff class? A Neff class, a 1-1 class is Neff if it can be represented by some alpha, some form alpha, such that for every positive epsilon, you can find a function f epsilon such that alpha plus IDD bar f epsilon is bounded from below by minus epsilon omega. So you should think about Neff, a Neff line bundle. If you think naively, Neff line bundle should be the same as you get a metric and the curvature is semi-positive. But this is not true. There are counterexamples to that. Instead, you have to make some approximation process. Yeah, you can find, for any given epsilon, you can find a metric on a Neff line bundle such a curvature gets as, how to say, the negative part gets as small as you want. Yeah? But for any epsilon, you find a new metric. Yeah, and that's the definition also here. So to speak, you can approximate by something whose curvature gets less and less positive. And omega is a fixed 1-1 form. Yeah, and of course here this requires x to be. So this is an F class. And that's a theorem of de Mailly from the 90s or so. I guess the Neff cone is a closure of the Kähler cone. In particular, I mean, for a line bundle, we have now two definitions of Neffness. The first definition is L is non-negative on every curve. And the other definition is as given as here. Just in the here. I mean, you can take the U to be the first Chern class of a line bundle. Yeah, and then you have get the second definition of Neffness. And de Mailly has shown that this definition agrees in the projective case. Yeah. So you have this algebraic definition on curves, and you have an analytic definition using curvature. And also what I already said, if we identify a curve with a current of integration over the curve, then we have an inclusion of n e bar of x and n a bar of x. So it's really the generalization. And then, of course, we know, I think this Kleiman already in the 60s, in the projective case, then an E bar of x is a dual cone to the classes of Neff divisors. And we have a similar statement in the Kähler situation. An A bar of X is a dual cone to the closure of the Kähler cone. So this cone of the Neff classes. Okay, now we want to approach this MMP. And in the MMP, in the algebraic case, you want to have Q factoriality. So what should be Q factoriality here? We consider complex space, and then we require, first of all, that some multiple of OX of MKX is locally free, as before. We fix such an M, and then we say that X is Q factorial if additionally every Weyl divisor is Q Cartier. I repeat that I cannot just take this definition because the canonical bundle is not Q Cartier. It might be not Q Cartier. So we have to be a little bit cautious here. Now we need to introduce a class of singularities. We want to have terminal singularities, and the definition is completely the same as before. Yeah, we have terminal singularities if and only if the following holds. You take desingularization with exceptional divisors E, J, and then the canonical upstairs MKX is a pullback of MKX downstairs, and then you have the sum of the lambda J, EJ, and the lambda J should all be positive. Yeah. So this is exactly just copy the definition from the algebraic case. So this is a category we want to speak about. So some basic facts very shortly. I've seen it already in many other talks. The terminal singularities in dimension 2 are smooth. Terminal singularities in dimension 3 are isolated. So this is our case. And they form the smallest category to run the MMP. And an example, for instance, is if you take this sum G squared, Cj squared 0 in C4, then you have the simplest terminal singularity. And an important fact which we use is that terminal singularities are rational. Yeah, so this is really a basic important fact. Okay. And I need another notion for line bundle, which we will later use, namely the notion of pseudo-effectivity. So I say that the line bundle is pseudo-effective if its class in N1 of X can be represented by a closed positive current. And this, well, so if you have the canonical bundle itself, canonical sheaf is not locally free, but then you take a multiple, yeah, and then it's locally free, and then you can apply this definition. So we have the notion of Kx being pseudo-effective or not pseudo-effective. And how to think about pseudo-effective line bundles. Let's say X is smooth, very simple situation. Then a line bundle is pseudo-effective if and only if L carries a singular Hermitian metric, H e to the minus phi. Phi is locally integrable. And then you have a curvature current, theta, and the curvature current should be semi-positive. Well, if you look at the people dealing with currents, usually they say current is positive. Yeah? But this is somehow misleading because then the zero current is also positive. Yeah? So I prefer to speak about semi-positive currents. And of course, I mean, if the line bundle has a section or a multiple has a section, then you get a singular metric with positive, semi-positive curvature current, so it's pseudo-effective. But a pseudo-effective line bundle might not have a section. Yeah, even a multiple might not have a section. It's only that for the canonical this should happen. Yeah? This is, so to speak, the miracle of the canonical bundle. I said this, if you have a section in some multiple, then it's pseudo-effective. But of course, pseudo-effective is very far from being nef. For instance, if you have an exceptional divisor, yeah, then this is pseudo-effective, but of course far from being nef. Yeah, and if X is projective, then the closure of the cone generated by the effective divisors is a closed cone of classes of pseudo-effective line bundles. Yeah, this is easy to see. Okay, and then yeah, we will distinguish between two cases, namely the canonical bundle being pseudo-effective and not pseudo-effective. Yeah, and the methods will be different somehow in some way. And so Kx not being pseudo-effective, then there's a theorem, usually called PDPP, saying if Kx is not pseudo-effective if and only if X uni-ruled, which means it's covered by rational curves. And yeah, I mean, so actually what in BDPP is proved, if Kx is not pseudo-effective, then you find a family of curves covering X such that the canonical is negative on these curves. And once you have this, you can apply a theorem of Miyaoka-Mori from the 80s that then X is uni-ruled. Yeah, so Miyaoka-Mori says if you have many curves on which the canonical is negative, then you find many rational curves. But this is characteristic P. There has been now it's a very exciting new development this year, namely there have been papers. This is for any dimension. We would see that in our case for threefolds, the same has been proved by Brunella. I will explain this in a few minutes. But now there are new preprints by Wen Hao and Zhao Pound dealing also with the higher dimensional case. So it seems that this is also true now in the Kähler case. And in the non-algebraic Kähler case, of course, they have an argument which does not use characteristic P. Yeah. But then, of course, I should warn you that they are dealing with non-algebraic Kähler manifolds. So it's not true that they find a new proof of Mori's theory for instance, for Fanos to get rational curves without characteristic P. This is not true. So what they use is a holomorphic two form. Let's see this. Okay. Anyway, we don't rely on Wen Hao and Zhao Pound because we will speak about Kähler threefolds only. Okay. Now, what should be the MMP program in Kähler geometry? So we have a compact Kähler manifold, or more generally, normal compact Q factorial Kähler space with at most terminal singularities. So there are two cases. If Kx is not pseudo-effective, then there is a bimeromorphic map from X to some X prime, such that X prime is a compact Kähler space with terminal singularities, which admits a Fano vibration of relative pk number 1. So the same statement as in the projective case. Yeah? You do something and you end up with a modified Fano vibration. And the other case is if Kx is pseudo-effective, then you have again a bimeromorphic map such that X prime is again in the same category and Kx prime is now nef in the analytic setting. And further, there is a procedure to construct the bimeromorphic map, namely by contractions of extreme arrays and flips. So in principle, this is the same setting as in the projective set case. So in fact, the bimeromorphic map should be constructed by contractions x to y of extreme arrays of the following types. Either it's a morphism contracting an irreducible divisor to something lower dimensional, or the exceptional locus has codimension at least 2, then one has to perform a flip. And the Fano vibrations, of course, they have relative ample anti-canonical bundle, So these are really Mori fiber spaces. The only difference to the algebraic case is that S prime is usually a Kähler space. Yeah? So you have final operations over something non-algebraic. Yeah, so we have projective morphisms. So it's I mean, fiber-wise it's projective, but the base not. And then, of course, you can ask what happens in the Neff case. I want just to mention this shortly. In Neff case, you have non-vanishing and abundance. So if Kx is Neff, then there should be some M such that some multiple of Kx is a section. Or, I mean, you can also formulate it up to MMP in the following way: Kx is pseudo-effective if and only if some M Kx is a section. But more should be true, of course, abundance. If Kx is Neff, then some multiple should be generated by global sections. So that's the picture, so to speak, when you end up in the pseudo-effective case with a minimal model. So what is known here? So in the projective case, of course, you know that MMP is known up to dimension 4, and in any dimension by Burkhardt, Cascini, Haken, McKernan, if X is of general type. In the Kähler case, we proved it in dimension 3. This concerns, so to speak, the existence of minimal models. What happens in the non-vanishing and the abundance case? Both are known in dimension 3, in the projective and in the Kähler case. But I think in higher dimensions there are some results, but I think one can say it's widely open. But I will not touch the non-vanishing abundance case. Of course, yeah, okay, so maybe some remark. So in principle, this is a miracle for the canonical bundle, yeah? In the analytic case, say. I mean, Kx Neff is defined by some very analytic property, yeah? So the class contains some positive thing. And then it should be true that Kx is Neff if and only if Kx on any curve is non-negative, yeah? Although we have very few curves. So for instance, this means that if you have a compact manifold, Kähler manifold without any curves, then the canonical bundle is always Neff. Automatically Neff. Yeah? Which in higher dimensions is, yeah. And more should be true, namely Kx is not Neff if and only if Kx times C is negative for some rational curve. Which is now, so to speak, up to these new results, seems to be true. Algebraic case, of course, it's true by a characteristic P method. But in the algebraic case, there's no purely argument over C known so far. Yeah, okay. Okay, so let me explain the rational curves in characteristic in Kähler threefolds without characteristic P. So we take a Kähler manifold or Kähler space with terminal singularities, which is not projective. Then you take a desingularization if you want, so let's say X is smooth. If you have a compact Kähler manifold which is non-projective, then you have a holomorphic two-form. This is an old theorem by Kodaira. So this can be seen as an embedding of the anti-canonical bundle in the n minus second wedge power of the tangent bundle. It's just linear algebra. So now if n is 3, n minus 2 will be 1, so we get a foliation. So now if Kx is not pseudo-effective, then Prunella has analyzed this foliation and he has proved that the closure of the leaves are rational curves. Yeah, by some lower dimensional, yeah, foliation techniques. Okay, so this is the argument why you get in the Kähler threefold, you get, if Kx is not pseudo-effective, you get many rational curves. Okay, so maybe I just spent 30 seconds on the case of surfaces. If you have a complex scalar surface, then, as explained many times, by contracting the -1 curves, we obtain a kind of minimal surface, so means no -1 curves. So this is the same in the Kähler in the projective case. Yeah. And then if X is uni-ruled, equivalently Kx not pseudo-effective, then you end with a P1 bundle over a compact Riemann surface. So this is of course algebraic. And in the case where Kx is where X is not uni-ruled, then Kx prime, the minimal model will be Neff, and then it's of course classical that some multiple is generated by global sections. Huh? And you're in the situation where the Kodaira dimension is 0 or 1. So this is completely clear and completely classical. So there's no difference in principle between the algebraic case and the non-algebraic case. Okay. So now, I mean, we want to approach this MMP, how to do the MMP, and yeah. So what is the method in the algebraic case? You first prove the cone theorem. Yeah? So you have this X, and then you have the cone theorem, which describes the structure of NE bar of X as the part where the canonical is non-negative, and then you have these extreme arrays. And the extreme arrays are generated by rational curves. And what you prove is that you have such an extreme array where Kx is negative, then you get a morphism with connected fibers from X to Y to a normal projective variety Y, which contracts exactly the curve which belongs to this ray. Yeah, so this is one of these basic results. And the key is the is-point-free theorem. So if you have this X and you take a line bundle such that L minus Kx is never big, then L to the M is generated by global sections if M is large enough. And of course, this is a point where the argument completely collapses in the Kähler case because you don't have these line bundles. If you have a big line bundle on a compact Kähler manifold, then the Kähler manifold is all automatically projective. Yeah? So there's no hope to do anything like that. So this is not available in the Kähler setting. Okay, so what can you do in the Kähler case? So let's first consider the case of a pseudo-effective canonical bundle. Yeah, so we assume Kx is pseudo-effective but not Neff. If it would be Neff, we are done. And then one of the following holds. This follows from a deep theorem of de Mailly-Paun, which again uses Monge-Ampère techniques. Then one of the following holds: either you find a curve where Kx times C is negative, or you find a surface S and a Kähler form omega such that Kx dot omega dot S is negative. And this you conclude as follows. I mean, how to use this pseudo-effectivity of Kx? You find a subvariety Z in X such that Kx restricted to Z is not Neff. Yeah. Oops. I wanted to go back. Yeah, I mean, Z would be here this one or this one. So at least you have something, some geometric object where the canonical bundle is negative. It's not Neff. And if the dimension of Z is 1, so you have a curve, you would like to move Z to obtain a surface. But unfortunately, this is not always true. One has to study so-called very rigid curves, which I will mention shortly. This is, so to speak, the curves which cause the difficulties where you have to flip. Yeah, I mean, in the flipping situation, you have a curve in the threefold which is very rigid, so to speak, no multiple moves, but you can contract the curve and then you flip it and you get rid of this difference. If the dimension of Z is 2, then Z is covered by rational curves. Yeah? So we really analyze this surface. And this relies on Buxon's divisorial-Zariski decomposition. And finally, I will come to this divisorial-Zariski decomposition in 1 minute. And one obtains finally rational curves where C where kx dot C is negative. Yeah, without any problems with characteristic P, but we take, so to speak, advantage of the low dimensions. Yeah? We have either curves or surfaces, and then it's very much more easy to deal. I mean, here in this very rigid curves, we also prove that these are rational. So what is the divisorial-Zariski decomposition in our case? So kx qkt and pseudo-effective, but this is a thing which works for line bundles, yeah? not necessarily for the canonical. So the canonical can be decomposed in a sum of lambda j sj plus n. The lambda j are positive real numbers and the sj are irreducible surfaces. And n is, so to speak, well, has a property that it's nef in codimension 1, which means that if you restrict n to any surface, then it's again pseudo-effective. And the canonical bundle restricted to the sj is not pseudo-effective. Okay, so the situation is that you find a lot of, or some surfaces where the canonical bundle is not pseudo-effective. And if you write down the adjunction, then you see that it's very likely that the canonical of the surface S itself should also be not pseudo-effective. Yeah, and think of a smooth surface, for instance, where the canonical is not pseudo-effective, then it's unimode. Yeah, so that's philosophically the argument. But of course, I mean, the surface Sj can be very singular, so you have to do a lot of work. But yeah. Okay, so a short moment concerning this very rigid curves. What is this? What is a very rigid curve? It's a curve where no multiple Chow sense moves. And what we prove is if you have a very rigid curve with kx dot c is negative, then c is a rational curve and kx times c is at least -1. But it's also negative. It's between 0 and -1. You may say that this is nonsense, should be always -1, but the difficulty is here that the space X might be non-Gorenstein. So if it is non-Gorenstein, then Kx times C is a rational number. And actually, if you have a Gorenstein threefold and the canonical is negative, then this all automatically moves. Yeah. So yeah. So the difficulty with these very rigid curves comes from non-Gorenstein points. In this case, then Kx times C is in general not an integer. Well, I used the name of a Chow scheme, but we are in the analytic case. So the Chow scheme does not exist in the analytic. Well, it exists in the analytic case, but it's usually called Barley space. Yeah, but it's much more difficult to construct actually. So there's a huge paper of Barley from the 80s where this space is constructed. Okay, but these very rigid curves have to be, so to speak, considered separately, and we prove that they can be contracted, and yeah, that's the case. Okay, so now what is the situation? To recall that, so we assume Kx is pseudo-effective, and then we have a negative extreme array in NA bar of X with a curve which is not very rigid. Then the Chow scheme has positive dimensions, so we really get a surface. We have a rational curve inside, and this rational curve moves. Okay, so now, yeah, we need a cone theorem. Yeah, I've said we want to take extreme ray inside NA bar of X. So we need the analytic version of the Cohen theorem. So we have a three-dimensional compact Kähler space, Q factorial with terminal singularities, and assume that Kx is pseudo-effective. Then there are at most countably many rational curves, Cj, intersection number is between 0 and 4, such that here we have this decomposition, which looks completely the same as in the algebraic case, with the only exception that NE bar is now substituted by NA bar. Yeah, so that's the difference. Okay. And now, of course, we do the same as in the Mori program. We take an extreme array in NA bar of X. Then we want to construct a contraction. And the contraction should have the property that the curve is contracted if and only if the class is in R. We are in a pseudo-effective case, so this means that phi must be bimeromorphic. And y should, of course, again have terminal singularities, and it should be Kähler again. This is an additional difficulty which arises in the Kähler case. Yeah, we construct some contractions. In the algebraic case, usually you have to get the line bundle automatically downstairs. Here, we have to prove that it's again Kähler, which really gives additional difficulties. So we fix an extreme array. Then by the Cohen theorem, we find a Neff class such that this ray is given as the perp of this alpha, so this set of all gamma, such that alpha times gamma is 0. And alpha is now kx plus omega, and omega is a Kähler class. In the projective case, we have a line bundle here, which is ample, and then you can use base point free theorem. But here, alpha is usually transcendental. So what do you do? Yeah, suppose that R contains now a positive dimensional family of curves filling a surface. So that's the most difficult case. The class alpha is Neff. And now we can use the theory of Neff reduction, which I will explain in a second. There's technical difficulties because the surface may be very singular, but yeah, okay, let's ignore that. And well, let's look at one case, namely that the numerical dimension of alpha of S is 1. This means that alpha is not 0, but alpha squared times S is 0. So this gives a vibration from S to some curve, which contracts exactly the curves in R. Yeah? So so to speak, the model case is that you have a threefold, you have a ruled surface in the threefold. So it's a P1 bundle over a curve. Yeah? So we are in this situation. And now the normal bundle of the surface along the fibers of the ruling is -1. And then you want to contract X along this map. Yeah? I will be more detailed in a second. So what we prove is that there's a normal compact threefold Y and a bimeromorphic map from X to Y such that phi restricted to this S is F, and outside nothing happens. So what is a Neff reduction? This is one method, so to speak, to construct morphisms without algebraic geometry. So we have a projective manifold, which is our surface, and a Neff class, but not a line bundle in general. And then we have the Neff dimension, numerical dimension. Yeah, doesn't matter. Alpha, that's so the number such that alpha nu is 0, is non-zero, and alpha to the power nu plus 1 is 0. And then there exists an almost holomorphic dominant rational map from S tilde to Y with connected fibers. Dimension is at least U of alpha, such that alpha restricted to the fibers is numerically trivial on all compact fibers. And for general points and a curve passing through the general curve with dimension f of c positive, then we have alpha times c is positive. So and somehow we have covering families. So this is something like this MRC vibration, which appeared, for instance, in various talks. Yeah? So we have families, we want to contract families on which alpha is 0. Yeah? So then you introduce some equivalence relation, and then you have to prove some things. Yeah, but it's not too difficult. So this kind of Neff reduction, I mean, in principle, you want to say if you have a Neff line bundle, then you get a morphism coming from downstairs, from S tilde to Y, such that L is, so to speak, 0 exactly on the fibers, somehow. This is generically true. While the map is not really holomorphic, it's almost holomorphic, which means that you have a lot of compact fibers. But this is not a very serious thing. So this is a technique we used several times. And yeah, so let me give some explanation on the proof here of this theorem. So we have the surface S, and we have the map from S to B. And we know that the general fiber is P1. The singular locus of X is finite. So generically, we have a P1 bundle of S circ to S, from S to B. Now we remove some singularities, and we have a P1 bundle. And what we know is that the normal bundle of this S is on the general fiber is -1. Yeah? So we remove some singularities. And then there's a classical theorem of Nakano from the 80s or 70s. Yeah, you have a ruled surface in the manifold, ruled surface S over B. The normal bundle is -1, has degree -1 on the fibers, and then you can blow down. Yeah, so X0 can be blown down along F circ. So you get a bimeromorphic holomorphic map from X circ to Y circ to normal complex space. Yeah. Okay. So this is Nakano. We cannot apply Nakano to full situation because the fibers get very singular and you don't know what's going on. The normal bundle is anyway. S is not a divisor. Cartier, it's not this Q Cartier, it doesn't work. Anyway, we have so we have this Y0, and what's easy to see that this extends to a compact Hausdorff space, and this phi extends as a continuous map. Yeah, we have an equivalence relation, you can just write it down. And what we prove is now that the complex structure extends to Y such that phi gets holomorphic. Yeah, you have finitely many fibers which are topological, yeah, finitely many points downstairs, and you have to extend the complex structures downstairs to get a holomorphic thing in total. And this reuses actually deep results of Bingener from the 1980s, algebraic case due to Artin. Yeah, so this, they looked at modifications and I don't want to touch that. It's very technical. And one issue, of course, which has to be taken into account is that we have to prove that Y is scalar. Yeah, but I think I don't want to touch the Keller this case. Yeah. I mean, what typically can happen is that if you take a contraction from X to some Y, then it could happen that y is only bimeromorphic to Kähler, or in the projective case, y is moisture on X explained by Mori also. Yeah, so for instance, you can have curves which are homologous to 0. Yeah, and you have to exclude this case. So you have to work really. Yeah, it doesn't come automatically. So the conclusion is we obtain this bimeromorphic model from X to X prime. And yeah, once the contraction is contracted, the first contraction is constructed, then the procedure is as in projective case. If ky is not nef, but pseudo-effective, then one starts again replacing x by y. Of course, the difficulty is that y might be small. And this happens exactly when the curves in the ray are very rigid. So then you think you run in a lot of trouble, but this is not true. Because, I mean, everything is locally algebraic. Yeah, you contract a curve to a point, to a singular point, and isolated singularities are algebraic. So it is clear that that everything is locally algebraic, and then Mori's theory just applies. Yeah, so you get this for free. Yeah, so the existence of flips, termination of flips is not a problem. Okay, so this is the argument if it is pseudo-effective. If it is not pseudo-effective, then we have seen that it's uni-ruled. And then, in principle, yeah, I have to be short here, we get an MRC vibration, which exists also in the Kähler case. Yeah, that's due to Campana. And you have to work with that. And in principle, what you do is, at the end, we get a Kähler form such that kx plus omega is pseudo-effective. Yeah? And then we run the whole theory before, replacing by kx plus omega. Yeah? So it's, yeah, I think, let me see. So we construct a pseudo form omega such that kx plus omega is pseudo-effective, and then we run some kind of minimal model program because we have this morphism here. And we work in principle with kx plus omega instead of kx. And then we prove a Cohn theorem and things like that for kx plus omega instead of kx. So that's the way to do this. Yeah, so we get a Cohn theorem, and then we construct kx plus omega negative rays and construct the corresponding contraction. And then at the end, yeah, so we can run an MMP such that kx plus omega times f prime is 0 for the MRC vibration, which we have. And then we need to prove an analytic version of the base point 3 theorem, which I probably don't state here. And at the end, we construct a morphism from X to some. Yeah, okay, I think I don't want to be here in detail. So at the end, we have to use the result of Nakayama running some relative MMP for projective morphisms. Yeah, I think it's will be too technical here to go into debate. Yeah. Okay. So that's in principle so some overview how the MMP works in the Kähler threefold case. So first we have done the case where K is pseudo-effective, and in the non-pseudo-effective case we used the MRC vibration and introduce a new MMP for not for Kx but for Kx plus some Kähler form. Yeah? Okay, and then I should say that Das, Haken, and U extended then the MMP for Kähler threefolds in ways. They considered more general singularities, D and E, and also treated pairs in the log case. And combination of work U, Sau, Höring, Haken, Cohn give a Cohn theorem, then also I think the Cohn theorem also in every dimension. But of course, how to construct a contraction is very unclear. So contraction theorem in higher dimension is an important problem. And as I said, contraction means also that you have to take care about the image to be. Okay, I stop here. Thank you for your attention.